that was rigid body equilibrium. Okay. So you remember when we started the coverage of rigid body equilibrium, way back then, I told you there are two objectives. Objective number one was what? You have a structure subjected to some forces. It is supported by some mechanisms, right? The objective was, remember, find all support reaction forces, right? Why? Because you have a rigid body, and the main objective to begin with is to find all forces that act on this structure, whether given, applied loads, or coming from the supports. So that was the first objective, to find all forces that act on this structure that is holding some loads, right? Then we wanted to move to the next objective, which is to find all internal forces. Unfortunately, before getting to this objective, we took a detour to cover centroid and moment of inertia. Now we are coming back, okay? So what do we mean by internal forces? Every structure is made of pieces, components, that are put together, connected together to make that a structure. A chair that I always refer to is the easiest, good example. Made of that seat, the legs, that platform, they're all connected together through some bolts or welded joints and whatnot to make that a structure to hold the weight of your body, right? That is a structure. In order to design that, besides the fact that we need to know what is the applied load and what forces from the ground act on that chair, we also need to find the right connecting devices, whether it's a bolt or a welding, to connect these pieces. So we need to know what forces those connections will be subjected to. In other words, at every point of connection or the joints, we need to know what internal forces act on that piece. That's what we mean by internal forces or forces at the connections. Okay? So that's that. Obviously, there are many different types of structures in the world, and in this course, we only focus mainly on two. Frames, we call them frames, or machines, which are the same, except that machines are structures that are not fixed to somewhere. You can move them around. A plier, a car jack, or a bicycle. These are all machines that are made of components subjected to loads, but they're not attached to something permanently, like a building or that light fixture. Okay? So frames and machines, and then trusses. There are other types of structures, or in fact components of a structure, that are very important. Unfortunately, we don't cover that in this course. For instance, beams that are very important structures or pieces of a structure. We'll leave the analysis for the next course. Okay? Before I start discussing or showing you how to attack this or tackle this objective, I would set up a table to summarize the attributes of these two types of structures, because it's important to know the difference between these two. So we're going to discuss frames and trusses. So what is it that differentiates between these two, or makes a structure to be a frame and make another structure to be a truss? First of all, the way these structures handle loads. That's important. In frames, loads can be applied anywhere along a member. Anywhere along a member, at a joint, doesn't matter. Okay, so that's important. Okay, they can be concentrated or distributed loads. A wheelbarrow is a frame. The load that you may fill it with a pile of dirt, that is a distributed load, right? That's your body sitting on that seat. That force is distributed over an area, is not just a single load, or making the assumption that you have a load that is concentrated at a point. In trusses, we make the assumption that the loads can be applied only at the joints. Truss is not designed to handle, for instance, loads along the member. Even if you look at a roof truss or any truss, a bridge truss, through that loads may be distributed over the structure, but the way we design it is that we, for instance, when you have a distributed load, we say, okay, part of that is assumed to be handled by this joint, part of it by this joint, and so on. We assume these loads are concentrated at joints. So that's as far as the loads and how you differentiate between a truss and a frame. Then it comes to the members. Okay. First of all, members can be of any shape. Straight members, crooked members, circular members, you name it. A pulley, anything. Okay. Second, are connected to each other at any point along the member. You don't have to connect, versus if you look at the leg of those chairs, which looks like this, you have two bolts connecting the seat to this is the member of that chair, like this, and the seat is connected here and here. So another member is connecting to this member somewhere along this member. Okay? Connections can be pins, fixed, etc. No restriction. You can weld the two pieces together, or rivet them, or bolt them. In trusses, it's completely the opposite. First of all, usually, not necessarily, straight members. Okay? Connected to each other only at end points. You cannot connect a member of a truss to another member in the middle of that other member. Okay. And connections, which are the only connections, are pins. That tells you something. Think about trusses. Members can be only connected at the two ends. These two ends are only pins, and no load acts along the member. Do you remember what we call those members then? Two force members. You get 2 points. Okay? That's important. So that you detect the fact that all members in a truss are two force members, and in frames you may encounter some members that are two force members. Okay? So with that said, how do we analyze these structures? Intentionally, I will start with frames. The book, most courses, they start with trusses and then go to frames. Frames are more comprehensive, more general type of structures. These are a special kind. So I will start from general, go to the special, or the not so general. I think that's better because it gets easier as you go from frames to trusses instead of the other way around. Okay? So with that said, okay, we'll start with the frames. So of all this stuff that you need to know about the frames, I do emphasize something as I introduce these steps that you definitely need to watch out for. In order to make it a sort of a methodical approach, not that I want you to memorize any steps, it's important to know what you're looking for and how you look for that, and also what is important, or what is the most important part of this analysis process, which I call that a structural analysis or rigid body equilibrium analysis, okay? Step number 1 is the same as what you had before. You draw the X, Y coordinate system. Easy, right? You need to set that up. You set up X, Y. And by the way, frames and trusses is what we are going to study the remaining of the course, nothing else. Friction, of course, is a concept we will introduce, but that's not really a sort of a new concept. Is a different way of looking at connections, how we are now ignoring, for instance, certain loads, which is friction load. We will introduce that. But as far as the structures goes, that's it. Through the end of the course, that's all we are going to be studying. So that's the step number 1. Step number 2, you do this, okay? You will take all members apart and draw members and supports, okay? And draw free body diagram of the entire structure and each member. Okay? There are 2 things that you have to remember, and they're extremely important in this step. In fact, I will consider that as a separate step because of the significance of that. And that is, watch out for 2 force members as you're taking these members apart. And let me remind you again what a 2 force member was. Only connected at its ends. Connections are pins. No load acts along that member. If you have all these 3 properties, that member is a 2 force member. What's about it? If you have a 2 force member, it is subjected to only a single load, single force, and that force acts along a straight line that connects the two ends. This force is equal in magnitude and opposite in direction at the two ends. Okay. Step number 3. Actually, also as part of step number 3, I would call that a subcategory maybe, or just a note. As you're drawing these free body diagrams, okay, pay attention to the law of reactions and actions, or the third law. That, what does that imply? If you have two members connected together, at the point of connection, there is one internal force. If you take these apart and you assume that from this member, a force is acting on that member, certain direction, same force, equal in magnitude, opposite in direction, is acting on the connected members. We'll get to that. Okay? So that's the first 3 steps. Step number 4. Okay. Actually, the first 3 steps are really the heart of the problem. Is 85% of the problem. Drawing all the correct free body diagrams. So up to here is really what you're doing is drawing a free body diagram is the heart of the problem. So this is 85%. Here is only 15%, which is all algebra. Okay? So step number 4, you start with a free body diagram with lowest number of unknowns, or the least number of unknowns, okay? Use equations of equilibrium to find as many unknowns as possible. You may not necessarily be able to find all the unknowns on that member, as many as you can. Okay? Then, step 5, move to the next member with the least number of unknowns. Okay? And repeat step 4 until you find all unknowns. Step 6, okay? When you try to find all the unknowns using these free body diagrams, the visual free body diagram, you realize that you always end up with one unused free body diagram. Okay? Use that to verify your answers. In other words, when you get to that stage that you have one free body diagram left, which you haven't used, all the answers that you have from the rest of the problem that you have found for this member, take summation of forces along X. They have to be 0. Summation of forces along Y has to be 0. Summation of moments has to be 0. If they're not, you made a mistake. And when you're done with that, step 7, you're done. Okay, so 7 easy steps. As I said, the intention here is not memorizing these, it's just a process logical process that you just follow. And I'm going to demonstrate that through an example problem. But do you have any questions first? Yes.
What's the last word in step 3?
Step 3, no load acts along that member. Sorry for that is not legible. Okay. Any other questions? If not, I started actually a problem in the other section, but since that problem, we couldn't finish it, it's a good idea if I can finish everything and start another new problem. So I selected another problem which serves the same purpose, but one fewer members. So I'm hoping that we can finish that, right, as an example, or a practical example. Demonstrate all of these. Okay? So let's see. Okay, this is the problem. You have a machine, or not it is, the frame, that looks like this. 3 and 4. And this is this is a good problem. And I think we can finish this. Okay, so. So you have a structure that looks like this. Okay. Let me label all these points. A, B, C, D, E, K, and obviously this is point 22. Okay, so you have a structure that is connected to this wall at point E with this pin. There's a roller here and there's another pin here. Okay, and we want to find forces that are connecting all pieces of this structure together, as well as the external forces. Okay, so the objective is to find forces at all joints or points of connection, external or internal. So as I said, step number one, set up an XY coordinate system. Step number 2, I still have it there. Take all members apart and draw the free body diagram of each member. So I'm going to start with this guy. Let's say this is connected at this point to a pin. So I do know that I have two unknowns here. I call them EX and EY. at this point, this cable is attached to this, so applies a force along that cable, T. And at point B, again, I have a pin. So there are two forces. I'm assuming that these are acting in this direction and this direction. Doesn't matter what directions you assume, except that remember this reaction and law of action and reaction. Okay? So, and it's a good idea to label these. I call this 1. You could have also started with the free body diagram, the whole structure. I'll leave that for the end. So let's move to the next member. I call this member 2. You have at A, right, a roller. That means you only have a force in that direction, perpendicular to the potential direction of motion. At point B, which is here, slightly here, remember the law of action and reaction. If you assume these are the forces at this point, internal, that act on this member, these are the forces coming from that member acting on that one. So at this point, B, on this member, forces have to be equal in magnitude and opposite in direction. I'm not sure if these are correct directions, but you have to be consistent. If you assume these are the directions for the forces assumed to act on this member, at that point, you have to use opposite directions for the same forces on the corresponding member. Now, at point C, again, I don't know. I'll just make the assumption forces are like this, Cx and Cy. And at point, somehow this is not labeled A, B, C, D, E, of, if I call it F and G. Okay, so what did I call this G? So at point F, again, is a pin connection. So I'm just assuming that there are two forces, right, like this and like this. F, X, F, Y. So that's member 2. That's this member and this member. Now, I have pulley F. That's member 3, right? There's this force and this force. We know those already, that this is 80 pounds. This is also 80 pounds. I make the assumption that these are internal forces on this member or in that direction. So should be like this, Fy and Fx, right? Now I'm going to make an observation here, okay? Look at this member. Member C, D. How many unknowns I have? A D is a pin. So how many unknowns I have? A D. It is a 2-force member, 2 points. See, I told you watch out for the 2-force members. If you don't, and make that mistake, believe me, you 99% of the time, you will not be able to finish that problem because you cannot find all the other ones. So this is connected only at the 2 ends, no load, pin connections. All these 3 criteria are met. So if there are member forces acting on this member, have to be, equal on the 2 ends. If I call this RD, this is RD, okay? Oh, I'm sorry, C. Yeah, that doesn't matter. Let me call that C for a reason, okay? So what I said here should be corrected also, right? So if that's the force from this member on that, in fact, these cannot be like this right? I have just one force of RC. So in other words, these two components, which you eventually resolve this into, are not independent. They're just one force, represent one force. So that is number 4. So we have 1, 2, 3, 4 members, but you have also one, yes?
I assume it's just like the other stuff, like you assume compression with respect to tension would just be negative.
You're right, good point. You know, you just make that assumption. When you solve the problem, it turns out to be negative, you know, that means the assumed direction is wrong. So, good point. I have one more free body diagram that I haven't used, right? And that's the structure as a whole. If I can cut this from its supports, right? And set up the free body diagram, right? Here I have EX, EY, okay? Here there was one force AX, and here I have what? Only one RD. Okay, actually, it's the opposite of that, because it is supposed to be active here. So I would call that free body diagram number 5. Okay? So let's see, 3 unknowns, 1, 2, 3, 4 unknowns, 1, 2, 3, 4, 6 unknowns, 1 unknown, and 2 unknowns. So which, that's, you know, I said step number 4, right? So I want to start with, okay, so I completed the step up to step 3, right? Now step 4. Start with a free body diagram with the least number of unknowns. Which one should I start with? Number 4, right? The only thing that you will find out is anytime you have a 2-force member. Obviously that member has the least number of unknowns, but then you discover that you already applied all the equations of equilibrium. So by using that free body diagram, you cannot find anything. Because there is no load acting on that member. You just have one unknown and 0 equations. Because you've already used equations of equilibrium. Okay? Yes?
At D, is there a reason you made it R?
No, actually, it should be the, no, actually, that's a good observation. I didn't realize I had considered it this way. It should be the same, right? Because that's the force coming from the support. Support is not an external, another member. So that is, I call that RC, right? So let me be consistent, call it RC or RD the same, okay? So what is the next best? Yes?
Number 3?
Number 3, yes. So I'm going to start with member 3, which is this pulley. So I write summation of forces along x is equal to 0, and fx minus 80 equal to 0. That gives me fx is equal to 80 pounds. As soon as you find one of the unknowns, mark that on every single free body diagram that it appears. So I have that here. So I put a check mark here, and I put a check mark here. Because I'm going to find out how many unknowns I have left on each free body diagram. That helps me that way. So then I write summation of forces along y is equal to 0. So I have negative Fy, right? And negative 80 equal to 0, which gives me Fy is equal to negative 80 pounds. Remember, the concepts we had already talked about in rigid body equilibrium holds here. Anytime you end up with a negative number, that means the assumed direction is wrong, right? So before you do anything else, make the correction. Okay, of course I put a check mark here, and here should be downward. Okay, and of course the correct path. So now we've taken care of this. So I'll just put a crossover so that I don't get confused. That's not a free body diagram that is useful anymore. And then go back to step 5, right? Start again with the free body diagram with the least number of unknowns. I have 3 here, 1, 2, 3, 4 here, 1, 2, 3, 4 here, right? So which one is the logical one? Just to go next. Number 5, because I have only 3. The rest of them have more than 3. So I will go to number 5. Free body diagram of the structure as a whole. And of course, we have not forgotten Mr. St. Erignon yet, at least I hope, right? So remember to resolve all forces with their components. And the dimensions are given. This is 4, this is 6, so this direction, right, is what? Is 2, 3, so that'll be square root of 13. Okay? So this would be what? This is 2 over square root 13 RC. This is 3 over square root 13 RC. Okay? So if I take summation of moments about E, again, remember, summation of moments is the best to apply. Oh, you know what? You didn't tell me something. I don't have 3 here, I have 4. 1, 2, 3, 4, right? So in all of them, actually I have 4. Not that it matters, but at least I know that I just have 4 there, 1, 2, 3, 4 here, 1, 2, 3, 4 here, right? So in all of the free body diagrams I have 4. So it doesn't matter which one I started with. So luckily I started with this one, okay? So if I take summation of moments about E is equal to 0, okay, I end up with what? I end up with, this doesn't generate a moment. It's only this one and this one. So if I take summation of moments here, they're going to be both be counterclockwise. So I have 3 over square root 13 RC times the distance of 8x, also positive, so 8x times 4, and the 80 pounds is negative and generates a moment of 80, and this distance is 6 plus 2, so it would be 8. And that's it, is equal to 0. So all of these can be divided by 2. So I have 3 over 2 square root 13 RC plus 8x, or no, sorry, 6. Don't want to make a mess here. So it would be 6 over square root 13 plus 8x is equal to 160. This is one equation. If I write summation of forces along y is equal to 0, I have 2 over square root 13 RC, okay, plus EY, right, minus 80 is equal to 0. So I have 2 square root 13 RC plus EY is equal to 80. So that's another equilibrium equation. And then I have summation of forces along x is equal to 0. So I have AX plus EX plus 3 over square root 13 RC is equal to 0. obviously I have 4 equations and 3 unknowns, right? So I cannot solve for all of them, right? However, as I said, exhaust all your options and do whatever you can, then you move to the next free body diagram. So I'm gonna go to this free body diagram right here, number 2. Okay, if I go to number 2, right? So that was number 2, right? I take summation of moments about B is equal to 0, and of course RC is resolved again. This is 2 over square root 13, or C, this is 3 over square root 13, or C. If I take summation of moments here, as you can see, I end up with only one unknown. And that will be what? 2 over square root 13 RC times the distance, which is, okay, this is what? This is 6, right? No, 3. Okay. This one and this one don't, I mean, this one, or this one don't generate any moment about point B, because they all go through point B. So it's only this guy, and that will be negative Fy, which we have found, right? Negative 80 times the distance from B, which is 325. I'm sorry, yeah, it's 4, because Fy is here. So this distance is 3 plus radius 4, okay, is equal to 0. So let's simplify that too. So RC becomes 160 square root 3 divided by 3, or RC can be evaluated. I think I have the answer here. RC comes out to be 192.3. Came out to be positive. That means the assumed directions are correct. Again, remember to check off wherever this force appears. So this is first of all useless. Now I have found this, and I have found this, right? Now I have a couple of choices here, right? Yes?
I think it's 92.3, this one.
Oh, 90 point-
It can't be more than 1.
Shouldn't it be square root 13?
Yeah.
Oh, square root of 13, I'm sorry. Sorry, square root of 13. So that is correct then? Okay. All right. So now you have a couple of choices, right? At this point, as I said, you either exhaust all your options, go to the next one. Here, on this free body diagram, right, here, I've only used one equation, summation of moments. You can now take summation of moments about y. I'm sorry, summation of forces about y. So you have 2 over square root 13 times RC, which is 192.3, right? Minus BY minus Fy, which is 80, is equal to 0. So you find By that comes out to By here, okay, 26.7. you can write summation of forces along X, but that you have two unknowns. What I would do instead, I can just go to whatever free body diagram I have used, and or equations of equilibrium that I have. So you have RC, right? You look at here. If I substitute RC here, that will give me a X. So I can quickly find AX, and AX comes out to be 160 pounds. Okay? So that's done, right? You can also use RC here. If you do that, you get EY from that equation. EY from that equation comes out to be also 26.7. Okay, AY was 20, AX, EY 26.7. Okay, 26.7 pounds. And then, now, you have found AX, you have found RC, so if you put RC here and AX here, that will give you EX, and EX comes out to be 0. It just happened to be that way. So keep track. I've used then this equation, okay? I've used this equation, and I've used this equation, right? Right? That means I've used the entire member 5, but I still haven't used completely this one, free body diagram. So I go back to this, okay? And if I go back to that, I have RC, I have AX, I can find BY, right? So if I write summation of forces along X equal to 0, that will give me BX. So you can see that I found all the unknowns. And I ended up not using one free body diagram, as I promised. You choose that to check, verify all the answers that you got. Okay? I'm sure this was quick way of doing a problem. I'm going to do a lot more, and we're going to spend actually probably 3 more sessions on this topic of frames. So I'm going to do a lot of problems. But as you can see, it's kind of an interesting process.